My name is Zack Loebel-Begelman.
And I'm Dustin Lyons. And we work with Credit Karma. Credit Karma, if you don't know what we do, we give free credit scores for around 60 million members today, which is pretty cool. And this talk is for people out there who've built some data pipelines using Scala, and maybe as your data is scaled, you found some issues maybe with throughput, or you found some bugs as you've scaled your data. And so this is sort of some of the learnings we've had dealing with that.
So what are we going to talk about today? We're going to start off with a brief history of the data architecture at Credit Karma. We'll talk about how, as that data scaled, we ran into some problems. We'll talk about the technologies that we chose to resolve some of those problems, how Akka Streams helped us. And then we'll also talk about some of the takeaways, the results and the learnings of kind of what we learned through this whole process.
Okay. So sometime in 2014, this is what Credit Karma data looked like. It wasn't the scale we are at today, but it was something like this. So we were dealing with a lot of analytics from browsers and phones and information about how people are engaged with our products. You think of a lot of events coming in over real time. And all this data is very semi-structured data, so this would go into Kafka, and then we ultimately needed some of that data to move into our data warehouse. So if you're not really familiar with Kafka, Kafka is essentially just a high throughput message queue that's built for real-time streams. So we had started to use Kafka, we loved that, and we needed some application to move this data into our data warehouse. So we built a Scala Akka application, essentially to import this data, subscribe to these topics in Kafka, and send this data over to our data warehouse, which at the time was Vertica. So 2014, fairly simple, it's kind of how it looked. Now in 2015, more people at the company, we need more tools to help us look at the data we're collecting, so we actually partnered with the company Amplitude. And at the time, we had much more data coming through, and so we needed some application, some service to help us import this data from Amplitude. So we had some success using Scala and Akka, importing data into Vertica, and so we built another service, Scala and Akka, to essentially connect to Amplitude's REST API, import the data from there, stick that as well into Kafka. And so, our experience, we built some actor systems here, but ultimately we moved to Akka Streams. And that's what we want to talk about today, sort of our experience with these two applications, why ultimately we landed with Akka Streams, and what that gave us. So let's look at the scale of the data.
No PII.
Oh yeah. No PII here. This is no financial information, no credit information. This is purely just anonymous data we're using in Amplitude. Just understanding how people are engaged with our products.
Cool. Uh-oh. So let's talk about the scale of the data. We introduced Kafka about when I started at Credit Karma in 2014. At that point, we were pushing approximately 162 megabytes every minute. And so we had grandiose expectations at the time. But the organization was still just getting used to semi-structured data in the pipeline and leveraging Kafka. So it's not a huge number, but it's certainly not a tiny number. So the next year, in 2015, that number doubled up to 324 megabytes every minute. We actually expected this. This is what we wanted to see. And this is why we wanted to use the JVM, use Scala or Java anywhere we touch the data pipeline, is because we want to be able to leverage that concurrency. It's also why we chose to use Akka Actors. We knew they would scale very well. See, Akka Actors leverage something called the actor model. The idea is actors are like a really heavyweight function. You send them a message, think of those as like the arguments to the function. It does something and sends another message, or does some side effect. The idea is that because it's the only interaction here is those messages, it scales really well across threads or even actually across boxes. You get all this out of the box. It's kind of a different way to think about concurrent programming. It's a push-based model. So can anyone guess what our data rates this year are? I'll give you a hint. It's another 2x increase. So we're up to 633 megabytes every minute. Again, not a huge number, but it's certainly non-trivial. It's not a Google or a LinkedIn, but it's enough for us to have to do some real work over and make sure that whatever we have scales along with it. And so I want to call out this number here, 750,000 events per minute. That's kind of our baseline rate of events coming in, that if we don't keep up with that number, we'll fall behind and we'll never catch up. So let's take a look at the actor system that we built to initially handle some of this. So you have Kafka at the top, and we have an extractor, a reader, deduplicator, and processor. So I want to take a second to talk about the constraints for this problem. Kafka is a durable message queue. It provides at least once semantics. That means that you're going to see every message at least once. Some of them you're going to see more than that. So you have to handle that. Kafka also handles we had it handling semi-structured data. It was JSON. Unfortunately, Vertica is a strictly structured columnar store, SQL ACID compliant. So we had to convert that semi-structured JSON into a format Vertica understood. The third constraint is that Vertica likes batch inserts in the hundreds of thousands or even millions. Kafka doesn't quite do that. That's a streaming platform, one event at a time. So those are the constraints to your problem. And actually, if you come into VR Credit Karma, I'll probably ask you to build a system similar to this. So let's talk about what everything does. The reader just accesses the Kafka iterator, gets a message, passes it on to the deduplicator. That determines whether the message is a duplicate or not. If it's not a duplicate, sends it along to the processor. The processor takes that JSON and converts it into a TSV. That TSV is then sent off to the extractor, which writes to disk, and if there's enough items on disk, loads that into Vertica, and starts the whole process over again. So it's a nice little flow we have here. The idea being we have one extractor, which spins up a number of each of these actors for every topic in Kafka, which equates to a table in Vertica. So if we had a new topic come online, just a config change, bam, we have another set of actors. It scaled really well and worked for our use case very well for quite a while. It worked so well, we decided to use the actor system for another use case that was coming about.
Yeah, so at Credit Karma at the time, we really enjoyed using the actor model in Akka. You know, as engineers, we could write fairly distributed code without worrying about all the multi-threaded work happening underneath. And so as Zack said, we did have some success with his application. And so when we were looking, as we scaled our data and we're working with Amplitude, we also used the actor model there as well. So just very briefly, I'll walk through what this application is. Essentially, these actors are the coordinator actor to pull the data out of Amplitude. They have a REST API, and every hour they make the last hour's data available. So we had something to kick off this batch process. And then we had what Akka provides is a router of actors, essentially allowing you to scale out work between one actors or a set number of actors you could describe. So we had a few routers of actors, essentially one set transforming the data from the schema that Amplitude provided into the schema that we needed internally. And then we also had a set of import workers to send this data into our HTTP ingest server. So at the time, you know, we were very happy. Akka's great. We shipped this. We were happy. Things were great. And then we started seeing problems in production. So I was getting paged at night, waking up, fixing issues. It wasn't that fun. So let's look at just a few of the issues we started seeing. So one of the main things we saw were futures were timing out. And when we dug into the logs and dug into the problems, we found that we had sort of a core issue at hand. There's only so many connections available to go outbound over our HTTP service. So as work was being queued up and pushed through our actor system, we were very quickly saturating the connection pool. And so all this work was waiting in memory, queuing up to go outbound, trying to latch on to a future that we used at the time we were using Spray. And there's only so many connections available. So these futures basically timed out as work couldn't be sent outbound. So really to get this thing to work overnight, we had to just basically increase this timeout pretty substantially. So that wasn't ideal, but hey, it worked for the time being. And so when we look back at this actor system we built, you know, there's some core things that we noticed. So you have this really fast thing happening in memory, right? So you have this transformations very quickly happening in memory. It's happening very fast. And then you have sort of a slower thing happening, which is using the network and going outbound and sending some data there. And then at the time, our HTTP ingest server was actually writing files to disk. And this was extremely slow, right? So we've since moved to talking to Kafka directly, but at the time, we were writing to disk, and you know, this was slow. So we see this problem of very fast work pushing down to very slow actors and slow work. So this wasn't ideal. And so another problem we saw actually was, we can spike up the timeout, right? We can have things queue up in memory and wait to go outbound to our HTTP server. But at any given hour, we're not really sure how much data Amplitude is going to provide. Some hours we'd see some burst of data. We'd have much, much more data from Amplitude, analytics from our browsers, our phones, that we'd get from that hour. And so even though the timeout was fine, we'd have so much work queuing up in memory that we'd essentially just, the heap space would blow up. So, trying to tune this in production just to get this thing to run, we ended up having to just increase the heap size, the max heap space, quite dramatically, which wasn't that great for other services running on the same box, because we're just eating up all these resources for work we didn't really need to do. So, I'm running into some scaling problems here, and I'm seeing I fundamentally got something wrong. And I think around the same time, Zack also started seeing some issues with the scale of the data.
So behind us, you can see a chart of, this is my application, reads from Kafka in the millions on the left, and minutes since the application starts on the bottom. So we, as you can see, this isn't great. Our 750,000 line is called out there, and most of the time you can see we're literally not keeping up with the data. So I had people at my desk asking, what's wrong, where's my data, and I'm trying to figure it out. And I realized we had a new schema or topic come online. Previously, our oldest topic was something on the order of 8,000 events every minute. This new schema was 80,000 events every minute, so an order of magnitude larger, and clearly the system couldn't quite handle it. I noticed it was paging. It almost seemed to freeze. It was using swap space. I wasn't sure what the problem was. Many of you have worked on the JVM. You might already know what this problem is. This is halting behavior. There's even a 20-minute period where we don't have any reads from Kafka. I'm banging my head against a wall. I have people at my desk. I don't know what to do. And so it was about this time, earlier this year, Akka Streams had just gone GA. And we thought, hey, this might actually be worth a look. So we took a look at it.
Yeah, so Zack and I were very tired of getting paged. No one likes to get paged. So when we started doing some research and seeing some things that we had got wrong, we discovered, and I think at the time Akka Streams was experimental. We kind of looked at it briefly, but we fundamentally started looking at Akka Streams to help us solve some of these problems. So what is Akka Streams? So earlier we're talking about we're having these actors push work to other actors, and Akka Streams flips that. It's this idea of pulling work through your system. So Akka Streams introduces this idea of demand, where it's an asynchronous, non-blocking signal, but it's a demand, a message to other actors to say, hey, I'm ready for work. So in my case, where I had slow actors, specifically HTTP work going outbound, as connections were available in my connection pool, it could request more work to be sent. So this formal concept is called back pressure. And this is something we had ignored in our first iteration of our services. And just to note, Akka Streams is still an actor system underneath. So you're still leveraging Akka and Akka Actors. It's just an API on top of that to introduce demand into your system instead of pushing a lot of work and overwhelming the other actors in your system. So this is built for high throughput, and it helps to prevent some bottlenecks that you would encounter without any concept of back pressure. So fundamentally, this was something we realized we had missed, and Akka Streams really helped to flip that paradigm for how we were doing our work.
So let's take a look at some of the fundamental concepts here. The core idea of a stream is it's something called a runnable graph. And it always starts with a source. The idea is that's kind of where the data comes from. So as far as the stream is concerned, it has 0 inputs and 1 output. The idea being that the data comes from somewhere external to the stream. Once you have a source, you plug that into a flow. The idea being a flow is a processing stage. 1 input, 1 output. You can make more advanced stages. You can have multiple inputs, multiple outputs. That's I think, a much deeper topic than we have time to get into. But you can have a one-to-one flow, and it actually provides a lot of nice things. Throughout this whole stream, you actually know the types all the way through, something that with raw Akka Actors you don't have. So you can have these compile time checks to say, hey, this was a sequence of J values, but I need it to be a byte string going over the wire, or whatever it might be. You just introduce a map to make those changes. That's a simple processing stage. And it always ends with a sink. The idea is there's 1 input and 0 outputs. It's the final resting place for your data as far as the stream is concerned, right? Is that it does something external to the stream. It writes to a file, or it creates a sequence that can be consumed from code elsewhere, external to the stream. So let's actually take a look at some of the specific API that they provide available. And all this is code you can use out of the box. Some of the built-in sources, you have from Future, you have a file, an iterator, actor ref, or even a sequence. Whatever works for you. This is all custom code that just you get out of the box. These are APIs that they just provide. Same thing with a lot of the syncs. You have head, sequence, last for each. Some of these should start to look familiar if you've worked with the Scala collections, which I assume we're at a Scala conference, all of us have. You have fold, and you can actually output to a queue. And I want to take a second to call out this actor subscriber and actor publisher. You have two ways you can integrate with actors if you're converting an existing actor system. You can just send raw actor messages, in which case you don't necessarily get back pressure. Or you have these traits you can inherit from. That was one of the things I used. I used the actor subscriber trait, and that way I got back pressure by just leveraging that trait. It's define how you want to handle items, how you want to handle your back pressure, and what type is exposed, what type the actor integrates with. Let's take a look at some of the processing stages. Again, a lot of the collections APIs, it's really actually all, I think, collections APIs. You have map, drop and take, drop while, filter. You know, these are all things that you can just use, no custom code necessary. You just call it on the stream, and it'll do that on items moving through. There's also these back pressure aware stages. This is where you know you're going to have something fast talking to something slower, and you want to handle that back pressure explicitly. So something like a buffer stage, for example. You can drop the messages, you can fail the whole stream, or you can begin to back pressure the rest of it. But it forces you to kind of think about, how do I want to handle this? What makes sense for my use case? So let's take a look at the system I had and how we had to convert it. So we had, the reason I think we ran into trouble is we had a decently fast operation over the network, reading from Kafka. We have these two in-memory operations that are also very fast. And then we write to disk, and then we upload to Vertica. So we'd actually created our own little version of back pressure because there's only one message in flight at a time throughout this whole flow. Nonetheless, we still wound up running into trouble. We'd actually were creating a case class each time and wrapping an object in a case class, passing it along. So every message we got from Kafka, we wound up making 5 case classes for. And we still wound up running into trouble. Let's actually take a look at how much simpler it is when we switch it to streams. We get rid of most of those actors, and there you go. We just have the stream. And so it's much simpler to reason about. We wind up having compile time checks, and actually the throughput improved significantly. Let's take a look at the code. And so what was a fairly complicated actor system before is now 10 lines of code that all plugs in and can be compiled. And you can be assured of the type correctness at that point. So we start at the top. We create a message parser. We mostly just converted that actor into an object that we leverage here in a map, but we provide the schema for the Vertica topic. You can see we're creating a runnable graph. We completely threw out the reader because we could just use a source from iterator. Kafka provides an iterator you can just use. We turned that into a type we understand. It's a map, Kafka message with metadata. We did have to write our own custom graph stage. That's what that via means, just because the deduplicator functionality didn't exist within Akka Streams. So that was really the only custom code we had to write here outside of converting some of our existing actors. And then again, we just actually map it. We use our processor. If you notice processor, process schema, we turn that into a write entry metadata, and then we send it off to our Vertica writer, which we had, like I said, use that actor subscriber trait, which means that this had back pressure all the way through. So that created our stream. That was our blueprint. But actually nothing happens until we got our start extraction call and we call run on it. At that point, resources are allocated and the stream's materialized, and that's when the work actually starts and the stream gets going. So this was a huge improvement, so much so, Dustin actually decided to do the same thing.
Shocking, we know. Yeah, in my case, I already talked about some of the fast and slow actors and how I had no back pressure out the system, but there's also a lot of some boilerplate code, right? We're having a lot of work segregated across a lot of actors. So for me, the big win was when I was able to consolidate some of that work into a stream. It's just much less code, much easier to reason about. So let's look at some of that. So in my case, the file source is the start of my stream, and so I'm dealing with a lot of files from Amplitude, and these files, I think we're
GZip.
Yeah, they're GZip files. I'm trying to understand how much data is today, but probably in the order of 40 to 50 million events an hour. And so, yeah, simple file source to start the stream off, and then you'll see that via stage. It looks a little confusing, but it's actually just using the new line to break the byte stream out into lines. And then essentially we map the object to something we know about, which is the J object. And then that transform stage you see there. Before there was a lot of work and a lot of boilerplate and lines of code just to simply do that transform. It just comes into one line, which is great. And then finally you see this map async. That's one of the back pressure aware stages Zack mentioned. So it essentially allows me to say, hey, use all the connections available. And you see that first bit, the count there that I include. Yeah, you'll see that. And basically that allows us to say, when we fill that many connections, back pressure. So it allows us to tune how many connections we want to have going out at any given time and have the stream provide some back pressure out of the box from that, which is really great. And then finally at the very end, you see we just do a wait for the next batch. So all the boilerplate code, that we had is very simple and easy to reason about in under 20 lines, which is fantastic. So I did mention that we had a lot of heap space to get this thing to work. So this is what it looked like before, which is not a pretty graph. So simply, you see a lot of work queue up in memory. The top line is the max heap space. And then very quickly, we fill up memory as we're waiting for this work to go out to our HTTP service. We probably could have done something in our actor system to account for this, but I think at the time we started looking at actor streams, or Akka streams. And so you'll see all this work queue up. And again, it's not always easy to understand how much data we're getting at any given hour. So this is 1 hour, but other hours you may have seen this just exceed the heap space. So you see it's a very large number, 23 gigs of heap just to get this thing to run. So after we switched to Akka Streams, it got much better. So here's about a third less heap being used, but you see the pattern is much more predictable, right? We're pretty consistent, we're pretty steady, and this is just showing the back pressure and what it did out of the box for us. Just having this data and the rate of work be consistent instead of these huge spikes just makes it much more predictable and much easier to work with. So that was a huge win for us. It's fantastic.
And so I was still haunted by this graph, right? We weren't keeping up. It was this halting behavior. It'd spike up and then do nothing. It took a few benchmarking runs, but I think I figured out what the problem was. But first, let's actually take a look at, this is our before. Let's see how it does with streams. Significantly better, right? Here's our 750 line. It's not even comparable. We spike up. We start at about 5 million, and then we spike up, and we're consistently between 8 and 11 million. So you can see our ingest rates have continued to go up. Luckily, we switched to streams, and we can keep up now. But this is a much better graph. This is consistently reading from Kafka pretty much as fast as it can. And people weren't at my desk. Things were much better. I was still bugged by that initial graph because I couldn't figure out what it was. Maybe you guys have. And we have a chart up here to show what the cause kind of was. So I'm going to take a quick pause here to talk about garbage collection. Right? It's the reason we all use the JVM, is that you don't need to allocate your own memory. It's managed for you. So we were using the G1 garbage collector, which has 2 styles of garbage collection, new gen and old gen.
Cleaning up new objects versus cleaning up old objects. Now, both of these are actually stop the world events, but
our old pre-Akka Streams is at the top, and our post-Akka Streams is at the bottom. So you can see at the top, we're doing these old gen collections, which are stop the world events. That means halt the application, do some pointer math, count all the objects, how many references there are to them, and then clean up the ones that aren't in use. We're doing old gen collections on the order of, 20 to 25 seconds. That's that halting behavior I was seeing. In fact, there's quite a few times on here where we're doing more garbage collection than we are actual work. I think it was creating all those case classes. I'm not quite sure, but whatever the case, it's the switch to streams, order of magnitude better. We don't even have old gen collections. We're only doing new gen collections, and we're on the order of 40 to 80 milliseconds. Several orders of magnitude better. No more halting, and the throughput, as you saw before, much more consistent. So people aren't at my desk anymore. Dustin can sleep through the night. I also can sleep through the night. That's my pajamas. And things were much better. So what are kind of the learnings and takeaways that we have here? Raw Akka Actors are still very powerful and come with a lot of tools you can leverage, but there's no back pressure. And so if you have fast actors going to slow actors, you can wind up getting into trouble, especially as you start scaling up more and more. That's when it can really become apparent.
Yeah, and so Akka Streams, is really built to optimize for high throughput. We still use a lot of just raw actors at Credit Karma for low latency issues. So we have a lot of services that run Akka Actors, fantastic. But if you're looking to solve really high throughput problems, you want to look at Akka Streams primarily for the back pressure you get. And again, like I said earlier, it's still built on top of Akka Actors. These are still some messages that are being sent, but it's just that nice, clean API on top of that, on top of Actors that give you the back pressure. And finally, don't be like us and try to build a high throughput system without this. You'll just start building Akka Streams yourself. So, thank you.